Gas chromatography and mass spectrometry is an instrumental technique that involves a gas chromatograph coupled to a mass spectrometer, allowing to separate, identify, and quantify low molecular weight, volatile, and thermally stable compounds in an organic mixture. This technique is basically composed of a stationary phase and a mobile phase. The stationary phase is a microscopic layer of liquid or polymer on an inert solid support inside a column. In GC, the mobile phase is a carrier gas. It is usually an inert gas like helium or a non-reactive gas like nitrogen. Other concepts are ionization and molecular ion. Ionization is the removal of a single electron of an atom within the molecule, forming a radical cation. The molecular ion is a molecule with one electron missing. It gives the molecular weight of the compound in the MS analysis. This technique starts with the solution being injected into the GC inlet, where it is vaporized and then swept onto a chromatographic column by a carrier gas. The compounds in the mixture are separated as the sample flows through the column. The separation is based on the interaction of the compounds with the coating of the column and the carrier gas. Then, the compounds eluting from the column are transferred to the mass spectrometer through a heater transfer line. At the entrance of the ion source, the compounds are bombarded by a stream of electrons converted to ions. Then, a mass analyzer, which is a filter, separates the positively charged ions. After the ions are separated, they enter a detector where the signal is boosted. Then, a computer receives all the information for the detector, records the data, and converts the electrical impulses into visual displays. A gas chromatogram and mass spectrum are obtained at the end.
The first main component of a chromatographer are gas inlets that are cylinders that supply the gas into the equipment. They usually filter gases to ensure the high gas purity. Pneumatic controls are required to regulate the gas coming into the instrument and then to supply the various parts of it. In an injector, the sample is volatilized and the resulting gas enters into the carrier stream entering to the column. Inside the column, the retention of analyzed molecules occurs due to stronger interaction with the stationary phase than the mobile phase. In the column oven, the temperature is controlled by a heated oven. The oven heats rapidly to give excellent thermal control. The detector responds to a physicochemical property of the analyte, amplifies the response, and generates an electronic signal for the data system.
The main purpose of this technique is the identification of unknown samples. This hybrid technique provides several benefits, enabling a wide number of applications. However, we will focus on a mix between the food and fragrance analysis and environmental monitoring categories. More specifically, the main functions that a gas chromatograph of mass spectrometry performs are the ones you see in screen. The instrumental analysis time usually is fixed by the duration of the gas chromatographic run, typically between 20 and 100 minutes. Food security is important since global population keeps growing. Therefore, crop protection products can help with crop loss reduction. However, this also means a potential harm increase for human health and the environment. This is the main reason of pesticide regulation, where this technique is highly applied. In order to prevent crop protection products to affect human health or the environment, it is important to determine if food products include harmful components such as pesticides. These techniques allow us to identify these irregularities, and you can see in screen some examples of GCMS applications. To conclude with these examples, all of them pursue the same objective of evaluating the quality of food or beverage products. This technique is a widely used option for this type of analysis and a number of applications, where trustworthy results are obtained, giving importance to several scientific variants.